argument principle is a very interesting statement that we can make about, again, meromorphic functions. Okay? Then the loop integral around some closed simple contour, I should say simple, should not intersect itself. It should also be taken in a positive orientation. All right, all these sort of default agreements that we've made. But that loop integral of f prime of z divided by f of z dz gives us something very interesting. It gives us 2 pi I times the number of zeros in f of z lying inside the contour minus the number of poles of f of z lying inside the contour. Multiplicity counts. All right? The reason why this works is because of something that you showed on your homework, I think, a while ago. Okay? Let's suppose that f of z has a 0 of order m at z naught. So then f of z is equal to z minus z naught to the m times g of z with g analytic at z naught and g of z naught not equal to 0. All right? And so now I can say, well, what about f prime of z divided by f of z? Well, that's going to be equal to m z minus z naught to the m minus 1 g of z plus z minus z naught to the m g prime of z divided by z minus z naught to the m g of z. Splitting this up, we find that the g of z cancels in the first contribution, and I'll have m over z minus z naught. In the second term, we just get g prime over g. Since g of z naught was not equal to 0, if I take a small closed loop integral around z naught, this part will be analytic. And so therefore the loop integral of this part will be 0 by virtue of Cauchy. This part will give me 2 pi I m. 2 pi I times the multiplicity of the 0 at z naught. Okay? If I now look at a meromorphic function over a larger region where I allow it to have multiple zeros, I can split that loop integral into a bunch of little itty bitty loop integrals around each of the zeros, and I'll just get 2 pi I times the multiplicity of the zero. If you do exactly the same thing, but make it a pole, so that now it's minus m, you'll see that you'll get minus 2 pi I m. That's why it's the number of zeros minus the number of poles. Okay? There's another way that we can interpret this, which indicates the reason for the name, the argument principle. All right? So f prime of z divided by f of z is the derivative of the logarithm of f of z. Okay? So if I integrate that using the fundamental theorem of contour integrals, what we'll find is that we get the logarithm of f of z at the end minus the logarithm of f of z at the beginning. Now, f of z had to be meromorphic. It didn't have any branch cuts. But the same is not true of log f of z, right? Log f of z can certainly have branch cuts. And so what we want to imagine is that as we go around the closed contour in here, let me actually do this. As we go around the closed contour in the z-plane, we can ask what happens to f of z. Okay? So here's my contour in z-plane. And maybe I've got some zeros. What that means is that in the f of z plane, I'm going to go around 0. All right. So I started here and I went around 0. Now, as I said, the function itself doesn't have any branch cuts, but the antiderivative will. And we can keep track of the argument of f of z as we go around. So let's see. 2 pi. 4 pi. 6 pi. 2 pi I times the number of zeros. Okay? If you have a pole, it means you're going to go backwards. You're going to go like around the origin the other way. If you like, you can think about it as going around infinity. All right? You're going around infinity in a counterclockwise fashion. So that is understood as going around 0 in a clockwise fashion. So that's why we're subtracting the poles. All right? But this can be used very effectively to count the number of zeros in a given function. It can only change by a whole number of multiples of 2 pi I. So I can compute it numerically. And I can't be off by 0.0001. It has to go up or down by a whole number multiple of 6.28 I. So I can see that numerically. And that allows me to do things like count the number of zeros in the Riemann zeta function, just by numerically integrating the zeta function's derivative divided by the zeta function around a certain contour. All right? Now, Rouché's theorem extends this. And what it says, it doesn't really extend, it's like a corollary to it in some sense. All right? So what it says is, if Rouchet was not interested in poles. So Rouchet is only going to use analytic functions. He's going to say, you know what, let's just say that the number of poles is 0. All right, they're analytic. And then he says, if f of z, or sorry, if h of z is always less than f of z in modulus on my contour C, it doesn't have to be true inside, just on, then f of z and f of z plus h of z have to have the same number of zeros inside C. All right, and the author of our book has given an excellent analogy to this. He says it's like you're walking your dog at night around a lamppost. Okay? If the leash that you're holding your dog on is always shorter than the distance from you to the lamppost, that's this inequality. All right, this is you plus leash. This is you. Then you and the dog both have to go around the lamppost the same number of times. It's not possible for you to go around the lamppost more times than your dog did. Okay, and that's because you had him on a leash. Anyway, that's that.